homework 2, okay? I don't have the due date. I said the due date would be 2 days after we finish the chapter in class. So, which is very fast, which is very quick, because it's a big homework, right? But what you need to do is you go back, we finish certain sections in class, you go back, solve the problems related to that. So the textbook splits the homework based on section. So if we finish the non-inverting amplifier section today, you go and finish the homework problems that are related to that. Believe me, if you do that, do the exercises, you understand what I'm saying, exercises in the chapter, understand what I'm saying in class, you should be fine for the exam, right? But if you keep it, you will never finish. If you keep the homework, if you use the same mentality of regular semester classes where the homework is due next week, I'll sit 2 days before and do it, it will not work. It really will not work with the way this, how fast this semester is going. So please just do that. That will be your studying. Go back, read the section of the chapter that we discussed, and the corresponding homeworks that are corresponding homework problems related to that section. Solve them, so that fine. We finish the chapter Sunday. You have Monday, Tuesday, and then Wednesday morning, the homework will be due, right? So I will announce it when we finish, but I don't know exactly which day we finish. So that's why I didn't put a fixed date on the homework. Okay, so let's go back to where we were last time. We were discussing common mode signals and differential signals. So we said that this is my op-amp device, and this will be the positive non-inverting input, and this will be the inverting input, and I will have V2 voltage here and V1 voltage here, and we called the voltage between these two the input differential voltage, VID. Okay, so that's what we call this input differential voltage. VID is the voltage between these two nodes, and it's equal to VID is equal to V2 minus V1, right? And then we said that sometimes you have extraneous signals that are coupled to your wires, to your inputs, that cause voltages that are applied to both input terminals. So for example, we said, I drew this last time as something that looks like this, right? And sorry, here I should draw a V1 source, and here a V2 source, for example. I did that last time, right? So plus minus here, plus minus here. So this would be a V1 source. This is a V2 source, right? So the input voltage, the voltage at this terminal is really this V common mode voltage plus this V1. And the input at this node is a V common mode voltage plus V2, right? So that's what we did. We did this last time, and we said that this common mode voltage in an ideal amplifier will not be amplified to the output, will not be transmitted to the output, right? Why is that? Because the output, the equivalent circuit for the output looks like a dependent source with gain A times VID. Dependent voltage source with gain A times VID that is connected to my output, and this is my common or ground point, and this is my V output. So V output is equal to A times VID. That is the V output. So it has nothing to do with this common mode voltage. So even though this terminal sees V1 plus VCM, this is the new sort of V1, right? V1 prime, right? And the V2 prime is V2, the old V2, plus this VCM, right? So the differential voltage is VID is equal to V2, so it's V2 plus VCM minus V1, so it's minus V1 minus VCM. That's why the VCMs go away, and we're only left with V2 minus V1, which are my actual signals that I had, right? So ideally, this is what's happening here. And we said that in this case, that means this op-amp has infinite common mode rejection capability. It is able to infinitely reject common mode. I'm only applying gain to my differential signal, which is VID. That's what this is, okay? So if this common mode signal was 1 volt, it's the 1 volt is applied to this terminal, it's also applied to this terminal, but never is seen here, hence never is seen at the output. We do not see that here. Okay, so that's this common mode business here. So they drew an equivalent circuit here. So again, these are the definitions that we for the differential signal. The common mode signal, the definition is half V1 plus V2. So if V1 and V2 have a common mode voltage of 1 volt, then you will have VICM is equal to 1 plus 1 divided by 2, which is 1. So this is how you calculate the common mode voltage in that case. Because you don't have, I drew them as separate sources, right? But they're not really separate sources. You have a wire, and this wire somehow has some coupling due to the electromagnetic or electric fields around it, and that has caused the voltage. So you cannot really measure that, by itself alone. So how would you figure out what that voltage value is? You would actually measure the voltage at terminal 1, measure the voltage at terminal 2, add them divided by 2, and that would be this common mode voltage, right? And we can here, for example, solve for, if you want to write V1 in terms of the differential voltage and the common mode voltage, we can solve for V1 or solve for V2. So if I do this, and this desktop background, so I solve for V1. So I bring, I'll solve for V1. So V1 is equal to what? V1 will be equal to V2 minus VID in this case. And then I plug that here. So VI input common mode is equal to half times, V1 is equal to V2 minus VID. That's V1 plus V2. So I'm left with what? Half 2V2 minus the input differential voltage, which is V2 minus VID over 2. That's VI input common mode. If I want to solve for V2 now, V2 is equal to what? VICM plus VID over 2. Right? So that's what they did here. They're just representing, rewriting, reorganizing these so that it becomes useful for something else we're going to look at later, right? So later we're going to be looking at the actual common mode gain, right? So they're preparing us for that by introducing some definitions and some terminology so that that the voltage at each terminal can be written in terms of the common mode voltage and the differential gain, and the differential voltage between the two that is due to the signal that you're actually applying at the terminals of your device. So an equivalent circuit for this equation or for this equation is what we have here, right? So the voltage at terminal 1 is equal to the common mode voltage here minus VID over 2, right? This is a flipped polarity here. So this is just some definitions. I'm just drawing an equivalent circuit of a definition here. Okay. So this is a simple equivalent circuit of an amplifier, and what they're asking for here is here, the internal circuit of a particular op-amp can be modeled by the circuit shown here. Express V3 as a function of V1 and V2. For the case of, they give you, and then, so first they want an expression for the output voltage. We know that the output voltage is equal to what? How do we calculate the output voltage? V3 is equal to what? V3 is equal to, it's a gain times the differential voltage, sure, but in this circuit, this is a specific op-amp now with a different equivalent circuit inside. So I gave you a simple equivalent circuit with one dependent source. Now they're giving you this example with a different equivalent circuit. You should be able to, because again, remember we said that we have a very simplistic equivalent circuit that we introduced in chapter 1 and different variations of it. And then we have more complicated equivalent circuit. So here, the idea is, it's equal to, V3 is equal to mu Vd. That's That's this one, right? And then VD is equal to what? Is this current here flowing through this resistor. So it's this I times R, right? So it's VD is this I times the R that we have here. So our objective is to calculate what is I. I we look at here. So we have a dependent source here that depends on the input, and we have another I here moving in this direction, also dependent on the input. Somehow this was the equivalent circuit, right? So this is GM times V1. This is GM times V2 current, right? So I have the current coming in is equal to the current coming out. This is Kirchhoff current law at this node, right? So GM times V2 plus I is equal to GM times, right? GM times V2. So this is coming in. Sorry.
Which op-amp is that?
They're just telling you this is an equivalent circuit for some op-amp.
Okay.
So GM times V2 that's coming in is equal to I plus GM times V1, right? So I is equal to GM V2 minus V1, right? So, and then VD is I times R. So V3 is then equal to mu times R times GM times V2 minus V1, right? And then they gave you some values for mu, GM, R, etc., and ask you to calculate the gain in dimensionless terms. I think so. Let's see. In terms, so they're given. For the case of GM is equal to so and so, R is equal to so and so, mu is equal to so and so. Find the value of the open loop gain A. But find the value. So this is the value of the open loop. This is V3. This is the output. But then the gain is what? Is the output over the input, right? So it's the input is what? V1 minus V2. So we take this. So it's V3 over V2 minus V1. That's the input. V2 minus V1 is input. That's your input, yeah. So V3 is the output, and V2 minus V1 is your input. So it's mu GM times R, and they've given you mu, GM, and R. So they ask you to calculate the gain A in decimals, and then they ask you to calculate the gain in dB. Okay. So now, okay. So everything we've been talking about was, we said that this op-amp is a nice device, right? It's a really nice and interesting device. But what was the main problem so far? I can only use it as a comparator. That is the big problem. It is useless, and it will saturate. If I use it as a comparator, if one of the terminals is larger than the other, it will either saturate to the positive rail, positive VCC, or the minus VEE supply, right, or something less than that. So it's not very useful when I have a device that can be used only in that fashion, right? So the idea is we need to find a way to use this device to create amplifiers. So what do? We put things around it. We will put circuits around it that allow us to do what? Control the gain. That's all we want to do. We basically want to control the gain. We want to control the gain, and its dependence on frequency as well. So, right, the gain will have, if there's no capacitors in the circuit, the gain will not be affected by frequency response, right? Because the open loop, the op-amp is an infinite bandwidth device. So theoretically, there's no dependence on frequency at all. But because we will add capacitors in there, then we will see that, fine, the gain will be dependent on frequency. So we want to control the gain as a value, and we want to make sure that we understand what the op-amp is doing for various input frequencies. That's the objective. So towards that objective, we have what is called the inverting amplifier configuration. So we will build, the first device that we will utilize is called, so we will build a circuit, and this circuit we will call it the inverting amplifier configuration. So inverting amplifier. So this will be the inverting amplifier configuration. So this is a circuit that has a building block of the op-amp. Okay, what does this circuit do? As the name will, as we will see later from the name, what the circuit will do is invert the input signal that we are sending into this device, as well as amplify it if we, depending on the amplification, on our design of the amplification gain that we want, right? So it will invert it, meaning if I put a positive signal, I will get a negative signal if it's DC, or if it's a sine wave, I will get something 180 degrees out of phase, not a cosine, 180 degrees out of phase, right? Because I'm just flipping the sign. That's what this will do. But it will also change its magnitude. So it's 180 degrees out of phase, and it can change the magnitude of the output as well, right? Can make it larger, can make it smaller, depending on how we figure out this. What is the voltage gain of this device, this circuit that we're going to add around this op-amp to make a new closed loop gain, right? We were talking about A being the open loop gain. So now we will talk about a new G or AC or ACL, whatever we call it. It's going to be the closed loop gain, right? So the nice thing is the closed loop gains are going to be defined. We're going to have a closed loop gain of 2, 3, versus before we had an open loop gain of infinity. What does infinity mean? Nothing, right? It's not defined. Now we want to add circuits around the device, the op-amp, and use the fact that it's a device with an infinite open loop gain to be able to develop circuits with a defined closed loop gain, right? So that's the objective. And one of the main things we will utilize to make this happen is what we call negative feedback. So we will be utilizing this negative feedback in all our circuits, right? What does this negative feedback mean from a circuit perspective? It means that I am feeding back my output into the negative input terminal. That's all this means. That's practically what this means. It just means that I'm taking the output, feeding it back here. But what is the effect of that? Versus positive feedback is something the opposite. The positive feedback is feeding the output back to your positive terminal, right? Is in general in control. Who took 420? Maybe just no. In general, in control or any physical system, positive feedback is not a good thing, right? In general, positive feedback is not a good thing. What does this mean? So typically, you want a system to have negative feedback so you can control it. So, for example, let me give you an example here.
What would happen if you put positive feedback?
So, that's what I'm trying to think of a physical example. So let's say you're driving a car and you're going up a slope, right? You will be measuring the car speed. You want to go at a certain speed, and you've decided you want to go, or the cruise control system. You've set the cruise control system at a certain speed, right? So what does the cruise control system do? It measures the speed of the car all the time, right? And then sends this to a computer. And this computer will decide to accelerate, add more, acceleration to the car or not, right? But it will do that based on what? It will do that based on the reading. So it will compare the measurement to the reading. Is it gonna find the difference between them, or is it gonna add them?
Find a difference.
Find the difference. Why would it add them? If it adds them, then Abdulaziz will go and take all these tickets and no problem, right? But it's different, right? It will actually find the difference, right? Because I want to measure my feedback speed signal, and then I want to compare it with my reference. So this is my reference speed, 200 kilometers per hour. It's still legal. So this is my reference, right? This is my reference, and then this is my measurement. This is my measurement. I want to be able to, I need to process this data somehow, and then take this data and send it to a controller, send it to me, the human, if I'm not using cruise control, I have cruise control setting in my brain. I want to go at 100 kilometers per hour. Then this is me, right? This is me, and then this is the car, right? And then I'm measuring the car speed, right? So I'm measuring the car. So can I draw a car quickly? Okay. So this is the car. So I'm measuring the car speed, and then I'm going to compare it to the reference that I have in my mind. And this comparison involves what? Taking the reference in as this is what I want. I want to subtract from the measured value so that the difference is something I have here. This I'll call the error, E, for example. This difference, if it's small, what do I need to do as a person? Me, this is me. What do I need to do? If the difference is small, I slightly press the accelerator. How about if the difference is big? I will, what is it,
Ram
what?
it.
Ram it down? I don't know, whatever it's called. I'm sure there's a vehicle terminology that I'm not aware of. So basically, I will try to push the accelerator down as fast, as much as possible, right? I'll push it all the way down, right? And how fast I push it down depends on me. If I'm an old man, I'll push it down. Okay, I know I need to go fast, but I'll push it down slowly. If I'm a young guy that I want to show off my car, my new Lamborghini, I will just ram on the accelerator, and I will do it very quickly, right? That's my transient response, right? You took 214 transient. That's my transient response, but it's based on what? This error signal, this input signal that was based on measuring these two, and this is called negative feedback. I am giving negative feedback to my controller. This is the controller. The output from the negative feedback is going to my controller, the human in this case, or the computer, right? So positive feedback will do something completely wrong. I'd be measuring something, I'm going to be adding it to the reference. So I will always be having this huge margin.
Do they use
No, positive feedback is not used. It's only used. There's only application, or at least the application of positive feedback that I know is for disturbance rejection. For example, let's say you have somebody talking in the classroom, right? Typically, you want students to come into the class. That's negative feedback. Somebody's talking in the classroom. What do? You want to kick them out, right? So this is a simple example, but disturbance rejection in control system is exactly the same way. So if I have some noise signal that I want to remove from, the so expensive, headphones, they do what? They do adaptive noise cancellation. So they cancel the noise that they measure from the ambient environment. That's all they do. When I was in College Station doing my master's degree, I think we did that in 448 lab or something like that. Like the adaptive noise cancellation algorithm, on a signal, like from a 314 perspective, we applied it. We did it in the lab, right? So you can actually do stuff like that. So that's one place where you want to cancel the noise. For example, you would do that. If you want to do something, and canceling noise is very important when you're talking about precision measurements, right? Anytime you're talking about if you want to measure position of something very accurately, you will typically use positive feedback in examples like that to eliminate the effect of external environments on the noise signal. So there are some applications. 420, I'm advertising for Dr. Hazm Nuno's 420 course. You should take it. So, okay, negative feedback. So this is what we're utilizing here. So from a circuit's perspective, okay, how does this negative feedback operate, and what's the consequence of having this negative feedback? So let's see. So let's look at before adding negative feedback, right? So what was happening? We had this op amp here, and let's say I ground this terminal for some reason. This is V2, I ground it, and this is V1, and I put R here. This is R1, and I put some VI here. This is open loop, right? This is plus minus V up. This is the op amp operating in open loop. What will the output voltage look like? A times V2 minus V1, right? This is always the output of the op amp, right? Always the output of the op amp, right? Okay, V2 is 0. V1 is VI, correct? So So V output is equal to minus A times Vi. Right? That is my V output here. Which is equal to, what? Come again. V naught over Vi. Yeah. V naught over, yeah. Or the other more important thing is, how about if you bring V naught over A here? What is Vi, or in this case V1, right? If A is infinite. Because I don't care about the sign. Fine, sign.
Would it be 0?
Yeah. So V1 in this case would be 0. Right? So that's one interesting thing that we're going to deal with.
So when it's negative feedback, if, for example,
So what did negative feedback do to this circuit? This voltage here is 0. This voltage here was Vi. Right? Here it's Vi. Right? Then I did some negative feedback.
plus the output voltage, the negative feedback, does the negative feedback add the output voltage to the input voltage?
It will affect it. I will see how it will affect it. I will draw an equivalent circuit now. Right? But what negative feedback, this is, do we agree that this is a large negative voltage? Here? This is a large negative voltage, right? If I take this large negative voltage, connect the resistor to it, and then measure at the terminal of that resistor without current flowing, I will still measure that large negative voltage. Now take that resistor and plug it in somewhere in the circuit. It's going to affect the voltage in the circuit. How will it affect the voltage in the circuit? Right? That's what I will draw an simple equivalent circuit to do that right now. So based on this, based on what we have here, we said that if, again, this is infinitely, yes sir. It's not open. No, it's not open loop gain anymore. The open loop gain will but this here, this op amp will still behave using open loop. I mean, this op amp is governed by the open loop gain, but this is the terminals here are now governed by, this is my input, this is input 1, this is input 2, right? And this is my output of this configuration. This configuration is not just an op amp anymore, right? It's an op amp with some circuits around it. So what are these circuits around it doing here? So that's what we're going to try to find out. So let's look at this. Kirchhoff voltage law, is a global law that will always apply, correct? So there's a loop here. This is ground. So there's a loop here, and there's a resistor here, and again, this is an op amp with infinite input impedance, correct? So the current into this op amp terminal is what? 0. So I here is equal to 0. I here is equal to 0, and let's say I would like to calculate the input current.
So because it has infinite impedance, that's why I would be.
Yes, because it has infinite impedance, I will be 0. I here also will be 0. There's no current flowing here or here. Nothing goes into the ideal op amp. No current flows into the ideal op amp here. Okay, but just because of the fact that nothing flows into it doesn't mean that nothing is going to be coming from my signal source here, right? So that's a different story. So let's first draw a simple equivalent circuit of something that is, something that is familiar to you. Okay, so let's say I have a voltage source here, and a resistor that I have here, and let's say I have another resistor here, and another voltage source, but opposite polarity.
How is this equivalent to that?
So here, this is my voltage source, this one. Then, yeah, the output, remember, this is an op amp. If the op amp is producing any output voltage, here we said that it has a value. Assuming the circuit operates, then the output has a value, right? So this value is between this node and ground. Okay? And this value we decided is negative. Right? It's a negative number. So I drew it this way. Right? And then what? So I have this voltage here, and then I have a resistor in series with it. Right? This is this resistor here. I'll call this R2 like they called it. Right? And then I have another resistor. You know, there's a loop here, right? To ground through this resistor, this resistor to ground. There's a loop here. I can solve the Kirchhoff voltage law says I can take voltage around this loop and solve. Right? We agree? And there's no current here. It's not connected anywhere. So
Yeah, where's the impedance coming from to make the current equals to 0?
from the op-amp internal
Oh,
circuitry.
from internal.
The op-amp internal circuitry, is such that it's as if I have this terminal connected to open space, right? Remember we said we put in chapter 1 we're putting this Ri, and we wanted Ri to be very big. Fine, I'm making this infinite. Okay, so this is what's making the I equal 0. But I have this loop here, right? This loop here is equivalent to drawing this circuit, right? So, and this is R1, and this is Vi, right? If this is the case, let's say R2 is infinite, before adding feedback, what was the voltage at this node? If I measure here with respect to ground. Before adding feedback R2, before adding feedback, what was the voltage here?
0 because
It's not 0. Vi or V1, right?
back in
What?
the same meeting we said that the voltage at the positive terminal is equal to the voltage.
That's what we're going to get to. That's what we're going to. I'm saying before adding the feedback. Before adding the feedback, what happened? Before adding the feedback, I had the voltage here equal to Vi. We agree? That was the voltage before I added the feedback. Where is this voltage coming from? Fine. I had no current flowing because this was connected straight to the op-amp. Since I had no current flowing, then the voltage between this node and ground is equal to the voltage at this voltage source. Right? So that's before adding the feedback. Now, if I add the feedback, so I remove this. Now if I add the feedback, then I have this circuit, like having this circuit. And this circuit will have some voltage source here that is equal to the output, and some resistor here, R2, and some resistor here, R1. So what is the voltage now at this node? The voltage at this node with respect to ground is the Vi voltage minus this drop. Right? This drop is due to current flowing in this resistor this way. I mean, this source is going to push current this way. This source will help push current this way as well. Right? It will help push current this way as well. If it helps push current this way as well, what happens to the voltage drop across this resistor? Does it increase or decrease?
Decrease.
Increase. Push more current, IR increases. The voltage drop is equal to IR. It will increase. The voltage drop that's opposing Vi will increase. Assuming I don't have R2 at all, then this current can increase easily. Right? If I don't have, if R2 is 0, R2 is not, it's there, but it's 0, it's equal to 0. If I don't have R2 at all, if R2 is 0, just a small voltage at the output, fed back, this means it's fed back. Fed back will increase the voltage drop across this resistor, opposing the voltage Vi, causing the voltage at this node, which is this node, to be equal to 0. Right? So that's what feedback did. Feedback made the voltage between these two nodes 0. There's no voltage difference between them. Right? So these two nodes, they're called, they track each other. And if I made R2 0, it's so easy to do that with a small voltage. How about if I put a value for R2? If I put a value for R2, then fine. This, I have to play with this V to make sure that I push enough current to bring down this voltage to a small value, right? But with or without R2, R2 is small or big, it's a different story, right? But it's at the end of the day, I can do that. I can now make this voltage very small. If I make the voltage very small, ideally 0, then what does that mean? That means that the output here is what? Equal to A times V2 minus V1. V2 minus V1 is 0, right? There's no difference between V2 and V1. What does this mean? It means that the output at the terminals here will no longer be controlled by the open loop gain of the amplifier, because the output is A V2 minus V1. It depends on the open loop gain of the amplifier multiplied by the voltage difference. I made this voltage difference 0. If I make this voltage difference 0, that means the output that is due to my op-amp's open loop, infinite open loop gain is useless, does not exist, it's 0, right? This also happens to be a nice linear circuit. Since it's a nice linear circuit, then superposition applies. So if anything else is causing something to be at the output terminals, then great, then the output will be some value. So, and this is what we constructed by adding components around it. We made the output affected by things other than the open loop gain. But these things were, these resistors and maybe capacitors later are put around it, and they benefit from the properties of the op-amp, having this infinite open loop, infinite input impedance, such that no current is flowing here. This is going to allow me to do things like, okay, if this is the case, how do I calculate my output voltage? My output voltage now is going to be this output here. This output here is equal to what? Kirchhoff voltage law is going to be equal to this voltage. And let's look at how current is flowing in this branch, right? So do we agree that this is an equivalent circuit for this loop out here? Right? For this loop, this is the equivalent circuit. That means that current will flow in from your sensor through this R1. It cannot go into the amplifier, right? It cannot go into the amplifier. Will go, where is it going to go? Is it going to go to the ground? No, this is not connected. They're virtually equal to each other. So there's a virtual short circuit between this node and this node. But they're actually physically not connected. So current's not going to flow here, right? The current will not flow here. But Kirchhoff voltage law does not say you cannot use this voltage between these two nodes to calculate this current. There's nothing wrong with that. This is a loop. This is a loop where I have an input voltage here, I have a resistor here, I have a voltage on the other side of the resistor. What's the voltage? It equals 0. Why? Because of the feedback. Right? So this is what the feedback bought us. It allowed us to easily calculate the current coming into the op-amp, even though the current is not going to flow from the source into this ground, into this connection, because this is not a physical connection.
What happens to the current?
Where does it go? You tell me. So here is 0.
Does it go back to the output?
Yeah, exactly.
That's how it gets its gain.
Yeah, exactly. That's where it's going to go. There is nowhere for the current to go besides up in this branch. So if it goes up to this branch, then current flowing this direction, I have a voltage drop in the opposite direction.
And since it's the same phase, it would just add to the...
Yes, it's a Kirchhoff voltage law. Here, then I can do Kirchhoff voltage law around which loop? Here. I have a voltage here, and I have a voltage here, and then this node's voltage is actually 0. Right? So, which means that V output plus this voltage is equal to 0. Or V output is equal to minus this voltage drop, the negative of this voltage drop. Right? So what is this voltage drop? This voltage drop is the current flowing from the input sensor and then up through this branch multiplied by this resistor value, right? So first, it's important to be able to calculate the current flowing in. So what is this current flowing in equal to? This current flowing in, I was able to calculate it by looking at the voltage across the resistor. The voltage on one side, the resistor has VI. And the resistor on the other side has 0. So what current is flowing through this? The current I input here is equal to VI minus V1. I will say it's V1 because it is V1, right? Divided by R1. V1 happens to be 0. So it's V2 over R1. That's II. How about the voltage drop across R2? The voltage drop across R2 is equal to II times R2, which is equal to, it's equal to II times R2. That's the voltage drop across R2. So it's equal to V2 R2 over R1, right? We said that, V output now. What is V output? V output is this voltage here. So V output, V output, this voltage here, plus this drop, plus the current II multiplied by R2. I go around the loop here, and then I find myself here. Here I know that my voltage is 0. Fine, I can go this way. I can do that. But, it's easier. You know that the voltage here is 0, so you stop here. So V output plus IR2 is equal to 0. That's Kirchhoff voltage law around this loop with a virtual connection here, right? So, which means that V output is equal to minus II times R2, which is equal to minus, what? V2 times R2 over R1. So my voltage gain is now the output over, it's not V2, why did I say V2? It's VI, sorry. Sorry, VI. I kept writing V2, right? It's VI, right? So it's output over VI is equal to minus R2 over R1.
You can use node voltage analysis and find it.
Exactly. You can. There's an easier way, but I have to explain, how it's happening first, right? But yes, we can. Let me draw that, and we explain it using node voltage analysis. So let me redraw, and do what Sheikh was suggesting. So this is VI. This is the output. This is R2. This is R1. This is VI. And plus minus. So what Sheikh is suggesting is, V output is equal to what? This is the voltage you want, right? So how would you suggest?
I did the node that's between R1 and R2.
Yeah.
And then I was like, minus V0 over R2 minus V1 over R1 is equal to 0.
Basically, just not voltage
V1
analysis.
R1, yeah. Because doesn't that
Zero,
node right there equal
It's
to
a 0,
positive
yes.
node?
Voltage here is 0. So what did you do? Sorry.
It's like 0 minus VI over R1
0 minus VI over R1.
over.
Over.
Sorry.
And then 0 again minus V0.
Minus
plus
0? Plus?
Zero.
Minus V0 over R2 equals 0. And if you rearrange, you will find it.
So basically this is the current. So you looked at the current flowing in here.
Not the analysis.
Okay.
Yeah, the R1 is divided by the 0 as well. Because
Shouldn't that be VI? Oh,
Yeah, it's VI. So yeah, my eye is a bit.
So the second one is
Perturb.
after, not
Huh?
The second one is after.
This one.
Yeah.
So you did.
get rid of the negatives.
It's not the analysis. So.
Yeah, it's fine.
Okay, makes more sense.
Makes more sense. I don't know, but you cannot do it unless you agree that there is a virtual short circuit here, and this virtual short circuit came from the concept that we added this feedback. I mean that's the whole. Yes, I agree. At the end of the day, everything we're going to do next is going to be 214. Everything we're going to do next, but it comes from our understanding that the voltage difference here is 0, and the current through here is 0, and the current through here is 0. If we agree to these things, then everything next, you can do it whatever way you want. Kirchhoff voltage law, voltage divider, it's all 214 after that. Right? So, but the understanding of the op-amp, fine. This is the new addition to to what we did. Maybe, I mean, fine, you probably did that in the last class, but we will build upon it and look at more. This is a simplistic view of it. We're going to be looking at more complicated views of the op-amp next year. So we now have an expression for V output over V input. So V output over V input is now equal to minus R2 over R1. It is this feedback resistor over the input resistor that I have. This is R2, this is R1, and where this was grounded, this is plus, this is minus, this is V output, right? So now the nice thing is my gain of the circuit is controlled by components that I'm adding. And you can buy resistors that are 0.5% accurate. You pay for them more, but you can do that, right? Versus before, the gain was infinite. What is infinite? You don't know, right? So this is why. So anytime you see negative, so in all our circuits, we will utilize this negative feedback. Why do you want to utilize this negative feedback? Because we want to bring down this differential input voltage, drive it as close as possible to zero. If we drive it as close as possible to zero, then the gain of my circuit is no longer dependent on the open loop gain, which is A. It's going to be dependent on the circuit around it, which you can solve using Kirchhoff's, nodal analysis, blah blah, whichever technique you want to utilize. Okay, so that's the story. That's where we're trying. That's what we're trying to do. So that's the analysis we just did. This is it's covered, is shown here. So all the analysis we did is shown here, and the equations were derived in the textbook here. So in this case, since my output is a gain multiplied by the input, for example, if I put, they're saying here, if I put a sine wave of peak to peak value 1 volt, what do I expect at the output? If the gain, if R2 over R1 is equal to 10, what do I expect to see at the output? I expect to see an output sine wave with a peak to peak value instead of 1, peak to peak value of 10. And I also expect that this sine wave is 180 degrees out of phase from the original sine wave that I've put.
Is it negative?
Because of the negative sign. Because of the negative sign, it's 180 degrees out of phase. Right? So this is what the inverting configuration does. Right? So it has some nice interesting things.
And so the positive one will also have the inverting. Non-inverting will also have an out of phase by 180, right?
No, the non-inverting, no. So inverting means it's not minus sign, 180 phase, 180 degree out of phase. Non-inverting means that the output and input will be in the same polarity.
Okay.
So, but there may be a phase shift, okay? So
But
it's,
not on it.
because maybe a phase shift due to frequency dependence. So far we did not discuss frequency dependence. We only have resistors around the circuit, right? So there's no frequency dependence, either in phase or 180 degrees out of phase, right?
Would you mind going up to that picture?
Yeah.
A little bit more.
This one?
So, okay, so that's why the current's zero, because that's a
It's an open circuit.
It's an open circuit.
Completely open circuit here. Ideally, right? Ideally it's an open circuit. Of course there is some impedance here. There is an impedance, but ideally this impedance is infinite here. So all of these characteristics, the infinite impedance, the property of feedback, that bought us simplicity in being able to control the gain of the output. The gain of the output is no longer A V2 minus V1. It's not that anymore. It's not controlled by that. The gain of the closed loop system is now minus R2 over R1. Yes, sir.
And the way that you like draw the ground,
Yeah.
like that.
Yeah.
Does it matter if we draw it like this or we make it all together?
No, it doesn't matter. No, it doesn't matter.
So it doesn't make a difference.
No. I mean, that doesn't make a difference on paper, right? In electronics, when you come build stuff, grounding is, it can take a whole class, graduate level on grounding.
I thought it would make sense if it was all connected but disconnected.
No. There's a big, grounding is a big issue. So I'm not an expert to talk about grounding, and this is not the venue to talk about grounding. So from a circuit's perspective, on drawing it on paper, fine, these are all the same. From building the circuit perspective, when you have, this is a simple circuit, right?
Yeah.
But when you have a very complicated circuit with a DSP, a signal processor, an FPGA with some analog signals and some digital signals, some high-speed signals, some low-frequency signals, high-magnitude signals or low-magnitude signals from a voltage perspective, high-magnitude signals or low-magnitude signals from a current perspective, all of this changes everything, right?
So
So
set up the ground each and every one of them.
no, I cannot comment on that. It's a science. It's not a, I mean, simple circuits, no problem. Just put everything, yeah, put a common ground, no problem. As I said, it only becomes important and very difficult when you talk about very complicated circuits like that. It's very I mean, it's very tough. I'm not an expert. I mean, it's an interesting topic. I would like to learn more, but you can only capture, you only have 24 hours a day, right? So it's anyway. So
I know, sir.
so now the nice thing is, so we developed some interesting story around the idea of utilizing the op-amp open loop gain as being infinite, right? This idea of the open loop gain being infinite brought us certain things that are interesting and simplified, gave us control over the gain of a circuit that we would like to develop. So I can now choose R2 over R1 to be equal to 2, 3, 4, whatever I want, right? So that's all nice, but of course in reality this op-amp has a finite gain, right? It's not infinite open loop gain. So A is not ideally, it's not really infinite, right? So it has some value, right? So in the circuit that we had here, originally we said that, so we said that the output is equal to A times V2 minus V1. V2 was 0, right? So V output was A times minus V1. So V1 was equal to V output over A, negative V output over A, right? So that's V1. If A goes to infinity, then V1 is equal to 0, right? If V1 is equal to 0, then it's like, these two terminals are shorted, right? That's what we did before. But in fact, if V0 or V output is a finite value, which we said is going to be a finite value. If we assume A is infinite, it's a finite value. It doesn't make sense to talk about this if there's no finite way to create a finite voltage output yet. So it's a finite value. So now let's say this, we utilize this finite value in the analysis. So now this voltage now is actually minus V0 over A. It's not 0 anymore. If it's not 0, that means that there's no virtual short between these two nodes, right? But can I analyze this circuit or not? Here, I have this, I have this, I have this, and I have this. Can I analyze the circuit? I can still analyze the circuit, right? Because now I know the voltage here, and I know the voltage here. I'm still utilizing the fact that the op-amp has infinite input impedance, right? I'm still utilizing the fact that these two terminals like floating in space, right? I'm utilizing that to use the fact that the I here is equal to 0. I'm using that fact, okay? So here I'm adding only one non-ideal characteristic. The non-ideal characteristic is open loop gain is finite. So I'm not removing everything that the op-amp buys me. I'm utilizing. I'm only taking it serious with the gain being not infinite. Okay, so the impedance is still infinite. So which makes my current flowing here 0, right? Now I can what can I do? I said that this node, the voltage at this node is minus V output over A from this analysis, right? If this is minus V output over A and this is VI, I can calculate I coming in. I can calculate as what? The voltage on one side minus the voltage on the other side, which is minus V0 over A. So over R1. That is the current coming into this device, into this circuit that I created. If A goes to infinity, what do I get? I get the previous analysis. This goes away, and it's the input current is equal to VI over R1. So which tells me I'm on the right path, right? So I input is equal to VI plus V0 over A divided by R1. Then, what is my objective? My objective, so now I can do what? Now I can calculate the voltage drop here, right? The voltage drop here is equal to what? I input, or I1 times R2. This is this voltage drop. V output plus this voltage drop plus this voltage is a loop, right? I can calculate. So, I mean, this is This is a voltage with respect to ground. Right? This voltage here with respect to ground. So this is the voltage with respect to ground. I have this current is going to flow in here, and then it's going to flow in through this resistor. So I know this voltage drop. I know the voltage at this node. I know the voltage here with respect to ground. It's V output. Or I want to calculate it actually. So V output is going to be equal to what? V output plus this voltage drop is going to equal to this voltage, or if I put it in the other polarity, it's plus this voltage, right? Is equal to 0. Right? So that's what we have in the next slide. Right? So here's what we have on the next slide. Sorry, on this book here, on the textbook. So V output is equal to this voltage, current flowing here. So voltage drop is the opposite direction. So this voltage minus this drop is going to equal to V output. So minus V naught over A minus the drop across this resistor is equal to V output. I've calculated I1 from the difference in voltage between VI and minus V naught over A. I've calculated I1. I substituted my calculation for I1 from before, which was this voltage difference, VI minus V output over A divided by R1. So I calculated I1. Substitute that here. That is I1 that we've calculated before, multiplied by R2.
Why is it minus I1?
Because this is a voltage with respect to ground, and this is in an opposite polarity. Right? So it's this voltage minus this voltage are equal to this voltage I have here. Right? So, and then it just happens to be negative. Fine. You just use it as a negative. This is a voltage with respect to ground. Minus, you remove some voltage drop from it. You remove the voltage drop across this resistor from it, and you will be left with the output according to Kirchhoff voltage law. And we had calculated I1 before from the voltage difference across this resistor. Okay? So this is the relationship between V output and V input and the resistors that I have and the finite gain of the amplifier. This is no longer infinite. Right? So I can rewrite this. I can write V output over V input, or we can rearrange it V output over V input as G. And then this will be the simplification of that, just rearranging the terms. So if that is the case, if A goes to infinity, what do I have? This term goes to 0. All of this term will go to 0. And I'm left with the gain V output over input equal to minus R2 over R1. Which is what I had before, which verifies my analysis here. Okay?
Do we want it to be?
It's large, but you want to be able to, like, if you see something at the, because it's going to affect. Remember, this superposition will apply, right? So, if this is a finite gain, right, what will it do to your output? If you just build a circuit like that and you measure something at the output, you want to know what this is due to, right? Is part of this due to the fact that you have a certain gain for the op-amp, and that this gain is not very, very large, right? If this gain is not very large, what is it doing? It's creating a term here that your ideal gain is divided by. So what is it doing? It's reducing your gain. It's reducing your voltage gain. So if you design something for a gain of 10, but you find that the output you have 9, right? Then what is the problem? Maybe this. This is one thing that can contribute to that, right? So this is one thing that contributes to that. So let me just do. This example is simple. Again, the input impedance, of course, in this case is equal to the input voltage divided by the input current, right? So input impedance is calculated. Remember, we said that the input impedance is, you put a voltage source. Experimentally, how would you measure it? You put a voltage source and current will flow. Take that voltage divided by the current, and you will have your value for input impedance. Since we have negative feedback, we said that this II is calculated from VI over R1 because of the negative feedback and assuming that A is infinite, right? These are the assumptions for this value of infinite input impedance that they're talking about. So, is this good or bad? I'll wrap up after, I'll stop after this one. So remember, my gain, so this happens to be the input impedance, right? My gain was what? Gain is equal to V output over V input was equal to minus R2 over R1, right? My input impedance is R1. What do you like input impedances to be for any circuit? If I'm connecting my transducer to it, to another circuit, what do I want this circuit's input impedance to be? Do I want infinite? Because I don't want this circuit to be drawing any current from me, the transducer. So I want this R1 to be, ideally I want it to be very large. But if I do it, if I make it very large, because this is what I would like to treat my sensor with, then what happens to the gain? I mean, then R2 has to be impractically large to have large gains for this circuit. Right? So that's the problem with this circuit. Right? It's a problem with this circuit, a limitation of this circuit. So the electronics guys, figured out a way to deal with that with this example. Okay, so try to go through this example and we'll get back to it tomorrow. As I said, guys, please start working on the assigned homework day by day. So today we finished all the way until we finished section, yeah, sure. We finished the non-inverting amplifier. The inverting amplifier, we even finished most of it. So the homework problems that were assigned on the inverting amplifier, go and do them, please. They are marked in the textbook. At least the PDF that I have, each section is marked. So each section it says, so for example, problems in this chapter, section 2.1 has problems 2.1 all the way until 2.7. We finished 2.1. Inverting amplifier, section 2.2. We finished most of that. So that covers problems 2.8 all the way to all the way to 2.43. Because starting 2.44 is the non-inverting amplifier problems. So you can basically do the first 4 problems of the homework, I think.
Do
Yes.
them without studying the problem.
You should do both.
We only have 24 hours a day.